Okay, welcome back, everybody. I hope everyone enjoyed their snow day on Tuesday. And regarding the assignments, so I'm like a couple days behind on the assignments, so the second assignment should come out either tonight or tomorrow, and then I'm going to adjust the due date to give you another few days to do it, or I'll make sure that it's not excessively long for the amount of time you have to do it. And so the first midterm is on the same, that hasn't moved, and so I believe that's scheduled for, let me just check, scheduled for the 12th. And so we'll basically do this next assignment, I'll post the solutions for everything, and then we'll have the midterm. And so, as always, once the assignment comes up, feel free to let me know if you have any questions or anything like that. And I'll give in terms of the midterm, I'll give some comments on what the structure of it is going to be probably next week. What sorts of questions, that kind of thing. Okay, so we're continuing with our work to come up with a set of equations that describe fluid motion that we can use to do predictions. And so we want to do things like numerical weather prediction. We want to predict what the winds or the ocean currents are going to look like in the future. And so what we've been basically doing is taking laws of physics and concepts from physics like acceleration and forces and that sort of stuff, and putting it together to come up with what will ultimately be the Navier-Stokes equation, which is the main equation that we use for predicting fluid flow. And we'll bring in another couple of related equations as well that sort of tie the whole theory together consistently. So last time we really talked about two major topics. One is sort of a theoretical topic, and the other was a concrete example. So we've been talking about partial acceleration. So we're sort of thinking about fluid mechanics from the point of view of we have our fluid, and we think of it as being composed of these little cubes, or whatever, they don't have to be cubes, but some small pieces. And those pieces are all moving relative to one another. And we want to consider it in terms of these little blobs of fluid, because then those things are very much like the baseballs or particles or whatever we're used to applying Newton's laws to. So we can apply F equals ma to a particle of fluid, whereas that's more difficult if we want to think directly in terms of a velocity field. And so over the last couple of classes, we came up with this formula here that says that if you have a particle, some fluid particle or a parcel that's embedded in a velocity field. So there's some velocity field u that depends on x and time, and we have a parcel is embedded in that velocity field. And what we're interested in doing is saying what's the acceleration of that parcel? So how is this velocity changing as it moves? And we want to do that because the acceleration is right in the F equals ma formula that we're going to apply to try to develop a prediction system. What we found was that by doing sort of some bunch of Taylor series kind of stuffed into one another, we derived this formula that says that the acceleration of a particle, and this is really a field, so this is the acceleration of whatever particle or parcel happens to be passing through the point x at the time t. The acceleration of that parcel is given by this combination of derivatives of the velocity field. The first term is partial time derivative that takes into account any explicit time dependence in the velocity field. And then there's this other term that has to do with the gradient. So the gradient has spatial derivatives in it. And then the gradient is the dot product is taken with the velocity field itself, which sort of tells us that if the flow is changing in a certain direction, and we're moving in that direction, then we're going to experience those changes. And so these two terms combine to form the total particle acceleration. We said that this construction of a partial time derivative and then this u dot grad spatial derivative piece here, it comes up so much that it's useful to define this as its own symbol. And so we call it capital D by dt is equal to the time derivative operator, partial time derivative, plus this u dot grad spatial derivative operator. We call that the material derivative. It's also called sometimes the convective derivative, total derivative, substantial derivative. There's different names, but we're going to call it the material derivative. That's the most common name. And you can expand this out. If you want to expand the dot product, you get three terms here. You get the x times the x component, that's ud by dx, and then v d by dy, and w d by dt. So you have four terms in total. We could also think about this same concept in two spatial dimensions. So if we didn't want to think about z, we just wanted to think about the xy plane, then all of this same construction goes through. You just wouldn't have this last term. You would just have the first three terms. And the interpretation of this capital D by dt operator, it's very important to not confuse the different types of d's. There's three different types of d's in this course: regular derivatives, partial derivatives, and then material derivatives. So the capital D is very important. And what this derivative measures is if you take capital D by dt of anything, like say, we're going to talk about salinity now in a minute. We started talking about salinity in the last class. What this material derivative measures is how that quantity changes if you follow a parcel. So you imagine you just have some labeled parcel, you paint it red or something that's flowing through the flow, and you're measuring if I keep my eye on that parcel as it's moving, how is its velocity changing, how is its temperature changing, etc. And so that's what this material derivative is used for. And because we're always thinking about building our physics out of analysis of parcels, it makes sense that this material derivative is going to come up all the time. And then we showed how this plays out in a concrete example, which we called the straining flow. So this was a simple one-dimensional flow, so just in the x direction, where the velocity of the flow, or the speed downstream, is just equal to a positive constant, which we call lambda, times the x coordinate. And in this case, we were able to solve, so the kinematic equation, just as a reminder, so the kinematic equation was that the dx dp so the rate of change of position of a material parcel is just given by the velocity field evaluated at that particle's position. So if you want to know where a parcel is going, you just look up where in the velocity field, what's the speed at that point, and that's how it's moving. And so in this particularly simple case, with a flow that's just basically accelerating faster and faster as you go down, or it's getting faster and faster rather, the rate of flow, as you go in the x direction. It turns out this flow is simple enough that we were able to solve the kinematic equation exactly, and we found that the positions of any Lagrangian parcel embedded in that flow goes downstream exponentially. So its time dependence is equal to its initial position. The position at any time is equal to its initial position multiplied by a function that's exponentially growing in time. And the nice thing about doing things this way was that it allowed us to calculate the acceleration of these fluid parcels that are embedded in this flow in two ways that are totally sort of independent of one another. First, because we have the trajectory, we know the position, you just take two time derivatives and that's the acceleration. And then the other way is to use this formalism of the material derivative and just take the material derivative of this flow. And what we showed was that in either method, we got the same answer back. And so the parcel viewpoint and the field viewpoint are totally consistent with one another, and often you can do a calculation two different ways and you'll get the same answer. Okay, and on the second assignment, you'll get a chance to do an example very much like this, where you can solve the problem two different ways: field viewpoint and parcel viewpoint, but for a flow that's slightly more complicated than this one, but still simple enough that everything can be solved exactly. Okay, so now we're going to talk today about another example illustrating how this material derivative is working, and then we're going to get on to a discussion of the forces that are involved in fluid mechanics. So starting with pressure forces, gravity forces, things like that. I'll just pause at the beginning. Does anyone have any questions about anything about the course, the review, or homeworks, or anything like that? Great. Okay. Okay, so salinity, so this is an example. Salinity in a uniform wall. Okay, so last time we had sort of a discussion right at the end of class, this was last Thursday, about what are the factors, the physical processes that affect the saltiness of the water? So the salinity or salt concentration in a fluid is denoted S of X, Y, Z, and T. And so we talked about a few processes. So some processes that can modify salinity. And they included evaporation was suggested. Rain or precipitation is another one. And then these two, evaporation and rain or precipitation, those are mostly going to be happening if that parcel happens to be at the surface of the ocean. So when it rains on the surface of the ocean, it can modify the surface salinity. But if you have a parcel that's like 100 meters down, that's not going to get affected by the rain, obviously. Maybe eventually down the line it'll have some influence, but not immediately. And so these are both surface phenomena. And so if we're away from the surface, these two things won't be acting, and so the salinity won't be modified by those. And another one we mentioned was inter-parcel mixing. This is also called diffusion of salt. And so this is the idea that if you have two parcels of water that have different salt concentrations and they're touching, they're physically right next to one another, that at the edge between those two parcels, molecular motions of the salt ions can kind of mingle them between the two parcels. And what that's going to tend to do is sort of make them equal. It'll try to bring them to the same salt concentration. And the same thing would happen, for example, with temperature. You have two different temperature cubes of water next to each other. They'll tend to equilibrate to the same temperature over time. But this process of interparcel mixing or diffusion, this is very slow. And so we're actually going to quantify later in the course when we start talking about specific phenomena and waves and stuff. We'll quantify exactly what do I mean by very slow. But what this means is that at least over relatively short periods of time, molecules, in water, they're bumping into each other all the time. It's a very dense material. And so because they're constantly getting jostled every which way, the rate that things spread out at is fairly slow. And so if we're looking on short time scales, like say the period of a wave or a few minutes or even an hour, this mixing of salt between parcels doesn't really have time to have much of an effect. So, so away from the surface, we can ignore all these factors. And so what that means is that to a good approximation, ocean water parcels conserve their salinity value. I.e., meaning parcel salinity does not change over time. And so, in our language of the material derivative, so mathematically, this property expressed as ds dt equals 0. And we call this equation material conservation of salt or salinity. Okay. So a very, very important distinction that I want to, we had to make sure we're really, really clear on, is this does not mean that the salinity field is constant at time. So so let's say we're looking, we're looking from space. Actually, there are ways to measure the salinity of the surface water from satellites. And so if we were looking at that, like imagine we could just see how salty the water is visually, like the saltier water looks redder or something like that. That distribution of surface salinity can still be changing all the time, even though we have ds dt equals 0, material conservation of salt, because each individual parcel of fluid can keep its same salinity, but if those parcels are moving around, carrying their salinity with them, the actual salinity field can be changing. And so even though we have conservation of salt on parcels, it doesn't mean that the salinity field is like uninteresting or not changing or anything like that. It can still be very, very complex, and we'll see later, you can get very, very interesting behavior, even if this fairly restrictive property is true. So there's a big difference between the salinity field being constant and the salinity being constant on parcels. Okay, so we can expand this out. And we would get partial s partial t plus u ds dx plus v ds dy plus w ds dz equals 0. Okay, so so this equation is actually a partial differential equation for the salinity field. So we have a time derivative here, and we have a bunch of spatial derivatives. They're all partial derivatives, so it's a partial differential equation. And this equation actually allows us, if we know the initial distribution of salinity, the initial salt concentrations everywhere, this equation allows us to predict what the salt field will look like in the future at every location. And so even though it's expressed as this simple principle that parcels don't change their salt, using this construction of the material derivative allows us to actually get a prediction system out of that. We can use this equation, and we'll see how, to predict what the salt field will be like at all future times. And we're just starting with salt because salt turns out to be a very simple one. Temperature is a little bit more complicated slightly. And so we're just starting with this sort of as a simple example to show how these material conservation principles can actually give us a way to predict what the distribution will be like in the future. Okay. So we can use this equation to predict S of x and t at all future times, assuming we know the initial distribution S of x and t equals 0. So like every prediction problem, we always have to know what the state of the system is at the origin, the original time, usually t equals 0. And then based on that, we can use this PDE to say what will it look like in the future. Okay, so example. Consider the uniform flow in 1D. U equals U naught x hat. So our velocity vector is just a constant u naught, and then 0, 0. So we have no flow, and so just like in the straining example, we're sort of thinking about flow just in one direction. So we have and the flow has no dependence on space at all. So it's just a constant flow. And so you can imagine this would look something like, here's x, and our flow is just a steady flow at every point, just moving to the right at the same speed. And let's take our initial distribution to be s of x and t equals 0 equals s naught times the exponential of minus x squared over L squared, I think is the example that I used. Yeah. Okay, and this what this looks like. So this is a called a Gaussian function, and so basically, if we were plotting s of x and t equals 0 versus x, it sort of looks like this. So it's just high salt concentration near x equals 0, and as you get further away from the origin, the water gets fresher and fresher. So, and this thing is embedded in a flow with speed u naught that's moving to the right. Okay. So does anyone have it's a good idea whenever you're going to do a physics problem to try to guess the answer before you actually do the calculation and have some idea of like what you expect the behavior to look like. That way when you do your calculation, if it looks like what you thought, then maybe you're on the right track. If it looks totally different, then maybe you need to reconsider either your calculation or your sort of thinking. Can anyone describe, just in words, what the future salinity distribution should look like in this case? What would we expect to happen, or how would the salt distribution look at some future time? So in general, I think sometimes these things are, because they're mathematical with functions and stuff, it almost seems more complicated than it is. But imagine, let's say instead of salt, let's say it was temperature. So let's say in the middle of this room at x equals 0, we've got like a blob of air that just happens to be warmer for some reason. So it's like warm here and it's cold on both sides. And then there's a wind, we put a big fan here, and there's a wind that blows this way. What's going to happen to the air in the room? What's going to happen to the blob of warm air?
It's going to move.
Yeah, move downstream, yeah. Right? Whatever the direction of the flow is, it's going to go that way. And so what about the salinity problem? So if we have a bunch of salty water at near x equals 0, we've got a current that's blowing towards the right-hand side of the board there. What do we expect if we were making salinity measurements, say 10 minutes from now? What would we expect the salinity field to look like?
Would it like distribute more?
So, yes. So in any realistic scenario, when you have fluid flow, whether it's in the atmosphere, if it's air, or in the ocean, we very rarely get a uniform flow, actually. It's almost always turbulent. So if you look, if you go walking around campus or anywhere, you often see like on the ground, like leaves are doing these little circles and stuff, and leaves are blowing erratically. Or if you look at snow, I find it really interesting to look at falling snow particles. If you look at any individual snow particle, as it's falling down, it often executes, it'll be like falling in some general direction, it's also executing complicated trajectory on the way down. So because of those sort of random, complicated motions, it is true that in general, whenever you put something in a fluid, it kind of disperses and spreads out a little bit. And so that's true. So actually that won't happen for our uniform flow. We're going to do the example mathematically. That's because our flow is like artificially perfect. But it actually, if it had any realistic complications, that would happen. But in addition to kind of like getting tangled at the edges like a cloud and sort of getting more complex and maybe a bit more diffuse, what else would happen if there's an overall ocean current that's blowing, that's flowing, say, in this direction? We could spread out, and also something else will happen that's simpler than spreading. So just like the warm air, when you put the fan, that side of the room is going to get warmer, right? Because the warm air from the center of the room is going to blow down to the side. So similarly, if we had an ocean current, and there was a salty pool of water in the middle, when the ocean current flows this way, it's going to push that salty water towards the left-hand side of the room. So if we're taking salinity measurements, if we're just over here measuring the salinity, and the salinity starts out being really salty in the middle, eventually we'll start picking up higher measurements of higher salt as the parcels that were originally in the center of the room move downstream into the place where we are measuring. And so when you have any kind of a structure, like a pattern or like a hot spot or extra salty water, and that's embedded in some kind of flow, the general behavior is just that it moves downstream. It just moves with the flow, and whatever parcels were in one location, they will later be found in a different location, having moved their value of salt with them. All the salt ions that are in some particular parcel stay in that parcel, and then that parcel moves downstream. So later when we measure over there, initially we'll find low values, because initially it was fresh over here, but then later the salt will have moved from the center of the room over to this side, and we'll measure higher values. So, so with that explanation, with that idea, could anyone suggest, if I wanted to sketch, so this curve here represents the salt concentration. So it's highest in the center, and then 0 or fresh water on the edges. So could anyone suggest to me, if I was going to draw a sketch of what will the salinity distribution look like at some later time, what would it look like based on this sort of discussion?
Like increasing towards higher values of x?
So you want it to look like, so you want higher values over here?
Yeah.
And when you say it's increasing, did it increase forever? Just as you go further and further in this direction, you just get more and more salty forever, or no?
No.
Yeah. Right. Yeah. Okay. So let me sketch it, and you can see whether this makes sense. So we initially have very salty water in the middle of the space. And then because there's a current going in this direction, I'm gonna suggest that what the distribution will look like in the future is very similar to the initial distribution, but just shifted downstream as it moves with the flow. So in later time, for example, our salinity distribution will look something like that. So we basically take our initial distribution and just shift it down in x, a certain distance, and how far we shift it depends on how much time we've waited. Because the longer we wait, the further this salty region, all these salty parcels will be shifted downstream. So this would be s of x, and say t equals 10 seconds or something. And so some future time, the initial distribution is just shifted downstream. And now your comment about will it get more spread out and diffuse? So if we had a realistic velocity field here and it was 3 dimensions, we had complications, the shape would not be exactly the same. The shape would also change. But if you just have a steady wind, it turns out that the shape of this doesn't change at all. It just propagates downstream. So our expectation is that the high salinity water parcels that are initially near x equals 0 will be pushed downstream, meaning to the right, by the background flow. So that's sort of what we expect. So mathematically, in 1D, our conservation equation becomes, so we have dSdt equals 0 equals partial s partial t plus u partial s partial x plus v partial s partial y plus w partial s partial z. But we have no flow in the y direction, so v is 0. We have no flow in the z direction, so w is 0. And u, in this case, so this is whatever the velocity field is. And in our case, u just equals capital U naught. It's just a constant number, 10 meters per second or something like that, some fixed value. And so our new equation, simplified, so it says, so our new equation, so this is the simplification based on our particular scenario of this equation here, dSdt equals 0, which is material conservation of salt. We get this equation, partial s partial t plus a constant value u naught times ds dx equals 0. And this is often called the advection equation. The term advection shows up all the time in fluid mechanics. And it really just means moving with the flow. So if something is advected, that means it's just following the flow wherever the flow is going downstream. And it's kind of like the word convection. So we're all familiar with convection that happens, for example, when you boil a kettle or whatever. And convection is really just the kind of advection, things moving around in a flow, that happens when it's thermally driven. When it's driven by strong heating or whatever, you get convection. But advection is the general term for when some substance moves with the flow. So mathematically, it's represented by this equation here. And so this is a fairly simple PDE. We have two first derivatives, and we have one constant coefficient in front that represents the speed of the flow. Okay. So now, what we're trying to do is we have also our initial condition x, s of x equals 0 is equal to s naught e to the minus x squared over L squared. So we have our PDE and we have our initial conditions. And so now we've used all this machinery that we built up of material derivative and so forth to convert this physical situation, the idea of having salty water in the presence of an ocean current, into a mathematical problem where we have a PDE that describes the salt concentration, and we have an initial condition, and then based on those two things, we can determine if we can solve this equation, we can determine what the salinity will look like at all future times. And so the way we're going to do this is generally PDEs can be tricky to solve. And so sometimes a good strategy is to just guess the solution based on physical understanding and then check that it actually satisfies the equation. And so that's how we're going to do it. And I'm actually going to sort of give a physical or logical based derivation of the solution to this equation. And then on the homework, you'll get to actually check by explicit differentiation that actually solves the equation. And any questions on the setup? solve this equation by sort of guessing. And assignment 2 will explicitly verify. Okay, so let's think of the flow as a line. So the flow is taking place along the x-axis. As we have here, x equals 0. We have our initial Gaussian concentration of salt. We have the idea that later on it's going to be somewhere else. And so if we have some position in the flow that we're interested in, we want to know the salt concentration at some position in the flow. So let's say we want to take some position x prime, and we want to say what is, how can we determine S of x prime and some time t. The idea is that t is greater than 0, so some time has elapsed, so things have moved downstream. So the key physical idea is that all that's happening in this system is that the parcels are just moving downstream with the flow and taking their salt values with them. So if we're looking at some position, and there's a parcel here at the position x prime at some time t, to know what that parcel's salinity is, all we need to know is where it came from in the past. Because we know all the salt values, we know the salt distribution at the initial time, and we know that the parcels are just moving and dragging their salt with them. So if we can identify where a parcel was at t equals 0, then it'll have the same salinity later that it had back then, because ds dt equals 0, the parcels are just keeping their salt content as they move along. So the question is, if at time t, a parcel is at position x prime, just some arbitrary whatever, 10 meters, 20 meters, whatever you might be interested in. So if a parcel at time t is at position x prime, where was it at time t equals 0? Does anyone have any idea as to how we might figure that out? So again, the idea is the flow is just moving at a constant velocity, so every parcel that's in the flow, that's in the fluid, are just all moving downstream at equal speed, equal to u naught. So if we know it's here at time t, how would we figure out where it was at time t equals 0?
Kinematics?
Yeah, that's exactly right. That's exactly right. Okay. So we can determine this using kinematics. All parcels obey the first year kinematics formula, where we have x equals x naught plus v naught t plus 1/2 AT squared is our classic formula from first year kinematics. In this case, our acceleration is 0 because we're just in a uniform flow. So nothing's accelerating, things are all moving at a constant speed. And so the position, x of any particle, let's say x prime, if we're interested in this particular particle over here that we're talking about, x prime, that position x prime is equal to its original position, the particle's original position, x naught, plus v naught, and v naught in this case is the speed at which everything is moving, and in our case that's u naught, so u naught times t. So as the situation evolves, different points are traveling downstream because their x coordinate is equal to its background is starting x coordinate, plus this increasing function of time. So as time clicks, as time ticks forward, this term gets bigger and bigger because t gets bigger, so this x coordinate gets bigger, so something is moving downstream. And so, so usually this is what we do. We have an initial position of a particle. We want to say, where is it going to be in the future? But in this case, we're sort of turning it backwards, and we're sort of inverting the problem. And we're saying if we know where it is at time t, where did it come from at time 0? So, so this is the position at time t, and this is the position at t equals 0. So we can rearrange. And write x naught is just x prime minus u naught t. So whatever parcel is at time t at position x prime, the initial position at time t equals 0 is given by this expression. Basically, we just have to subtract off the distance that it traveled since time 0, and just sort of run the kinematic equation backwards and say where did it come from at the initial time. So because parcels maintain their salinity as they move, we can now write down the solution to our PDE, which is S of x and t. So we can recall that the original salinity distribution was equal to S naught times e to the minus x squared over L squared. L is a constant. And so our distribution at some later time is just S is equal to S naught times the exponential of minus, and instead of x, we're going to put x minus u naught t all squared divided by L squared. So essentially, we've just said, to figure out what's the salinity at some particular value, x, subposition, we said rewind that position by u naught t, which is the distance it would have traveled at time t, and read off from the initial distribution what that parcel's salinity was at the initial time. So to check that this formula actually solves our PDE, that we have the mathematical solution, explicitly calculate or compute partial s partial t equals partial by partial t of s naught e to the minus minus u naught t squared over L squared, and u naught ds dt, sorry, u naught ds dx, which is equal to partial by partial x of s naught e to the minus x minus u naught t squared over L squared, and show that partial s partial t plus u naught partial s partial x equals 0. So to check, so we basically just use physical reasoning to come up with what we think the equation is, the solution is. But of course, it's important to check that actually it mathematically satisfies the equation that we wrote down. So usually solving differential equations is quite hard. But if you have a candidate solution, checking if it's right is pretty easy. Just take the derivative, plug it in, and you should get 0 equals 0 at the end. And so just to make sure that we satisfy this equation, we just have our explicit formula here, take the time derivative, take the space derivative, and, oh, I'm sorry, there's a u naught here, right? Take the space derivative and multiply it by u naught, and when you add those two results together, everything should cancel perfectly, and you should get 0. And so that's going to be on the second assignment, just checking by hand that this works. So really this example is just about illustrating what material conservation means and what that results in for how patterns change over time, the salinity pattern, temperature pattern, whatever. And the general idea, which is very, very simple, is that if you have a flow, then the pattern just tends to drift in that direction. And so here, this formula does this explicitly. Okay. Any questions about that example or any of this, the first bit of the class? Yeah.
Oh, can you explain the last derivation, like the last two steps?
This part here or up here?
Yeah.
Down here. Yeah. Okay. So it's very much like if you were taking a course in differential equations, right? So you have some differential equation that's like, for example, you have an equation like y double prime plus 2y prime equals 0, or some random thing you get out of a book or an assignment. So if you were, so to solve this requires special tricks, like you have to know like how to deal with each type of equation and so on. But if I just told you, here's y of x, an explicit function, right? Is that a solution to this equation? Well, you could just take two derivatives and then add that to twice times the function itself times the first derivative. And if that all adds up to 0, then you know you've got a good solution. So you can just check by explicit calculation. And that doesn't need any tricks, because you can always, integration is hard, but differentiation is difficult. You can always take the derivative of any function, chain rules, stuff like that. So that's what we're doing here. So we had this PDE that came from capital ds dt equals 0, which expresses the physical concept that as parcels move around, they keep their salt value. And just based on the simplifications of this problem that we don't have any velocity in the two other directions, we just get this equation, ds dt plus u naught, which is a constant, times ds dx equals 0. We said that's called the evection equation. And so what we actually did was, so there are, if you look at a book on partial differential equations, there will be techniques in the book to solve this equation. But this class isn't about PDEs, it's about fluid mechanics and oceanography. So what we did instead was use physical reasoning to come up with a hypothesis, a guess for what the solution is. And just based on this physical chain of reasoning that's over on those two boards, we came up with this formula. But now we had to know, does it actually solve the equation or not? We think it makes sense, but does it actually work? And so just like in this example, if you have a candidate solution, you can just explicitly differentiate and calculate the terms in the equation and check if it works. And so that's what I just laid out here, is that there's two terms in the equation. One of them is ds dt, the other one is u naught ds dx. And so you could calculate these two derivatives explicitly. It's going to involve some chain rule stuff. And then once you calculate this and you calculate that, if you add them together and they give 0, so things will cancel, the term minus itself, stuff like that, then if that's equal to 0, then we know that we have a good solution. So that's the whole idea. So we used physical logic rather than mathematical tricks to get the answer. But then to verify that it actually solves the mathematical equation, we got to plug it back in the end, take the derivatives and make sure we get 0 equals 0.
Thank you.
All right. the next section, all these examples, the last two examples, the straining flow example, where we did the kinematic equation. In this example, we're all just about getting a general intuition for how do things move when they're in fluid flows. But so now, we're going to start moving towards not just how do things move in a flow that we know, but what actually determines the flow itself. So how forces and things work to actually determine fluid flows, rather than just how do quarks and so things like that move when they're embedded. So next section is forces in fluid dynamics. So we want to apply Newton's second law to fluids, fluid parcels. So we have some parcel, it's got a velocity, it has some small mass. We often write that as dm. The little d here just means we're thinking of an infinitesimal mass. You could also think of it as delta m. These are sort of interchangeable notations, but it has some small mass. It might have an acceleration, and then there might be various forces, like maybe there's gravity, F equals minus mg z hat or something. Various forces acting on this parcel. And we're going to sort of combine them up and try to write Newton's laws, and then that's going to end up giving us this Navier-Stokes equation. Basically, is just a fancy version of Newton's law applied to fluid parcel. So Newton's law is F equals ma. And so for our parcel, the parcel mass so generally, when we have a fluid parcel, we think of the sides, we usually think of it as a cube, and the sides are of length delta x, delta y, and delta z. So our volume of our cube, we call that delta v, and that just equals the product delta x times delta y times delta z. And so delta x, delta y, delta z are just all small numbers, like maybe one centimeter, some small amount. We've got a little cube, and so it's got a small volume, and the volume of a cube or a rectangular prism or whatever is just the product of the three lengths. And so our mass, delta m, is equal to the density of the parcel times delta v. So rho here, Greek letter rho, that's the fluid density, and that's defined as the mass divided by the volume. So typically, rho for seawater is roughly 1,025 kilograms per meter cubed. So we usually use units of kilograms per meter cubed for seawater density. And the number might look a little bit peculiar because you might be used to seeing 1,000 as the density for the density of water. For example, in chemistry courses, things like that. Density of water is usually 1,000. So can anyone tell me why is it a little bit higher for ocean water?
The salt water.
The salt, yeah. There's actually if you have 1,000 kilograms, it's actually there's a lot of salt in it. If you have 1,000 kilograms of water, there's 25 kilograms of salt. It's quite a bit. So this extra 25, that's due to the salinity. And the density is really a field. So rho equals rho of x, y, z, and time. So if you look at, so in general, the seawater has density of about 1,025 kilograms per meter cube. But if you look at different places, the density is slightly different. The density of seawater tends to only vary by a few percent from location to location and from time to time. And those variations are due to variations in salinity and also variations in temperature. And pressure also plays a role, but it's mainly temperature and salinity. And we're going to come back later in the course and talk more in detail about how the density of water was determined. So, but anyway, so we're just introducing the concept of density. And so if our parcel is, we have some small parcel with volume delta V, then our mass is rho of x and t times delta x, delta y, delta z. That'll be some small mass. So we have, so F equals MA, and we wrote M is rho delta V, and our acceleration is du dt. That's the capital D by dt, the material derivative, that always measures the rate of change of whatever it is with the flow, and so the rate of change of velocity with the flow, that's acceleration. And so we can combine these, and we get rho times delta x, delta y, delta z. That's our mass, times du dt equals F. And so this is really the starting point for, so this is mass times acceleration for a parcel. And this is forces on the parcel. And so for the next little bit, what we're going to work on is talking about what forces there are. We'll come up with some mathematical formulas for what to put in here for F that will give us an equation, a partial differential equation that will allow us to predict this velocity field based on the forces. Okay. So we will next investigate forces F to produce a PDE that can predict U. Okay, so the most important so the force in fluid dynamics that's most essentially fluid physics is the pressure force. Pressure is a fluid property that squeezes submerged objects. So for example, if we have a parcel of fluid or a cube or anything, and it's submerged in the water, so we have the surface of the water up here, then pressure acts to squeeze in on any surface that's inside the fluid. So, for example, we have some cube. Then pressure forces will act on all of the 6 sides of this cube. We would have a pressure force that I'm calling on the left, the left-hand side. There's a pressure force acting on the right-hand side. There's a pressure force acting on the bottom, acting on the top, and acting on the front and back. And what I'm writing here is capital F for force with a vector sign, subscript P meaning it's the pressure force, and then also indicating the direction, the side of the cube on which this force is acting. And so we all know from experience that pressure varies from place to place. And in general, we know that as you go into the very deep ocean, the pressure gets super, super high. That's why, like for example, submarines and stuff like that can implode sometimes under the high pressure. And on mountaintops or whatever, once you're up in high altitudes, the pressure tends to be very low, the air is thin, it's hard to breathe, you need oxygen tanks, stuff like that. So, so the pressure is defined as the force per unit area acting on submerged surfaces. That's what we often write. P is equal to the pressure force divided by the area. And you can think of pressure, so we're talking here about fluid pressure, but any force can exert pressure. So for example, if you have a book or whatever, the stapler laying on the table, there's a force that's acting on the table that's equal to the weight of the stapler, the mass times gravity, and that's distributed over the sort of footprint of the stapler, and so there's a pressure, the force of the weight, divided by the area over which it's distributed. And so in some locations in the ocean, pressure can get very, very high. And I'll see if I can bring this in next time. So my wife, who teaches in biology, when she was doing her PhD, her supervisor was one of these people that worked on deep sea submersibles. So you may have heard of, there's a submersible called Alvin. There have been a bunch of documentaries about this. Basically, you can go down in it and use it to look at like hydrothermal vents and like cool organisms that are on the seafloor. And they do this fun thing where if you have here's the surface of the ocean, here's your submersible with your people inside. What they do is on the outside of this, they have a little rope and they put styrofoam cups that are attached to little ropes, and they go down to the bottom of the ocean and they come back up. And the pressure is so high that the styrofoam cups come up like all tiny, like they're like shrunken to 10% of their original size or something, so they're just smushed by the pressure. And I believe she has one of these, so I'll probably try to see if I can bring it in next time to show it around. So the point of that is that pressure just squeezes everything in from all sides. Okay. So I'll just make the comment here. Pressure is also a field. So our pressure is equal to pressure that depends on x, y, z, and t. So example, pressure is high in the deep ocean. Pressure is low, high in the atmosphere. It can fluctuate from place to place and time to time. And then this is one of the key ingredients that exerts forces on our parcel. So it exerts 6 forces on all sides of the cube. Can anyone tell me, so we'll pick this up again next class. We'll talk about exactly what is this F, how do we build a force F out of this pressure field. But can anyone tell me from a fundamental physical perspective, why is it that when you put something in water, it gets squeezed? What is the origin of the pressure force? What's really sort of happening that causes that?
Microscopic collisions of the particles.
Microscopic. So can you just elaborate a little bit more? So why do microscopic collisions exert a force?
Well, you're changing the momentum of the particle itself. So if you were to hit a wall arbitrarily, the velocity changes, but the momentum has to be proportional to the rate at which it changes, right?
Yeah, that's right.
So 2 equal forces.
That's right. So basically, so it's kind of like Newton's third law or whatever, right? Like every action has an equal and opposite reaction. So so at the microscopic level, pressure originates from molecular collisions. So, for example, let's say we have a wall to the edge of a container, or this could be the edge side of a ship or whatever, and then the water is made up of all these little tiny particles, and those particles are moving randomly to a large extent. So it's sort of it's an interesting juxtaposition you sort of have to hold in your mind. When we talk about the velocity field or the flow or like an ocean current, we have this idea that the water is moving in some coherent direction, like downstream or whatever. But there's also another kind of motion. So when you have, say, an ocean current that's blowing, say, to this side of the room, what that means is that all of the water molecules are sort of moving in that direction. But they have actually 2 different kinds of velocity. They have their coherent velocity, which is the sort of the average velocity that they all have, all moving collectively in one direction. But then on top of that, they have what's called a thermal component. So there's basically a random jittering motion that coexists with the coherent motion. And so, in addition to any coherent motion that there might be, these particles are also all kind of moving in random directions, and they hit off of each other all the time. And so what happens with pressure is that if one of these molecules hits the wall, it can't go through the wall, so it bounces off. And so its momentum has changed. It initially had a momentum, initial momentum was mv, say, x hat, and then as it leaves, its final momentum might be, say, negative mv x hat, if it goes in and then comes out. And so its momentum has changed, which is equivalent to being acted on by a force. And then so by Newton's third law, that particle also exerts a force on the wall. Or you can just think intuitively, if I throw a baseball at something, it exerts a force. Okay, so next time we'll talk a little bit more about the molecular underpinnings of pressure and how it connects to other thermodynamic quantities like density and temperature. And then we'll derive the formula for the pressure gradient force, which is the first and most important force that's going to go in on our right-hand side of Newton's law. Okay, so we're going to pick that up on Tuesday. Keep an eye out on Brightspace because the assignment should come out tomorrow, if not this evening. And always feel free to reach out if you have any questions. Okay.